Hello everyone, welcome back to another session of building estimate, how to calculate the quantities of different item of works. So students, in the previous sessions of the building estimate or the lecture series of the building estimate, we have covered up the topic of long wall and short wall method and the center line method. So today in this session, we are going to learn fundamentals of reinforcement calculation and a numerical or the calculation based on RCC beam. So starting with the fundamentals of reinforcement calculation, let us begin with the first fundamental. So the first fundamental of reinforcement calculation is weight of the bar. Yes, students, have you ever felt that the steel which we are using is placed in meters or in feet, but while you order that steel, that should be in kilograms. So we need to convert our quantity into weight. So we need to find the weight of a reinforcement bar. So there is an empirical formula, as you can see here, d square by 162. This d square by 162 gives the weight of per meter bar, where d is the diameter and that should be in mm. So, for example, what will be the weight of 7 meter long 16 mm diameter bar? So we know the formula of per meter weight of a reinforcement bar is d square by 162. So 16 square by 162. That will give us 1.58 kg per meter. That means weight of 1 meter of 16 diameter bar is 1.58. Now here our length is 7 meter. So we just multiply the 7 into 1.58. That gives us 11.08 kilogram. So that is how we can find out the weight of an reinforcement bar. Students, I would like to mention a point here that reinforcement quantity is one of the important quantity in our civil engineering. As a junior engineer or as a senior engineer or as a project manager or whatever role you can say, you must need to aware about the steel quantity because it is one of the high cost material of our civil engineering. So if the quantity varies by 1 or 2 tons, that can be a heavy loss. So steel quantity is one of the accurate quantity in the civil engineering. Moving forward, let us see the different weight per meter of different diameter of bars. Here is the table. So as you can see, I have prepared a table of per meter weight of different diameter of bar. For an example, for 6 kg, it is 0.22, 16, we have just learned that 1.58, for 12 mm, it is 0.89 and so and so. So, you can do it by d square by 162 whenever you are calculating in a numerical, or you can directly remember these values to speed up the quantity. Let's move forward to our next fundamental. Students, think that what if there is a 90-degree bend in our reinforcement bar? See this figure. If there is a 90-degree bend or L-shaped bend in our reinforcement bar, we need to calculate that extra length of that bend. Generally, as in the theoretical aspect, it is considered as extra 4D. So if the vertical length is L and that bent up is considered as 4D, so the total length will become L plus 4D. On site or in general practice, minimum 300 mm bend is always provided. Whenever you have to bend your reinforcement bar as L, minimum it should be 300 mm. So I hope we are clear about this. Now, moving forward, what if there is an 180-degree bend in your reinforcement bar. 180 degree looks like something this. So whenever there is 180 degree bent up in the bar, which is also known as hook, that hook is approximately 9D in the length of 9D. So if the original length of the bar is L, the hook of only one side hook, you have to add 9D. So your total length will become L plus 9D. But generally that hook, 180 degree hook, is provided on the both the side of the bar. So as you can see in another figure, this kind of scenarios generally happens in our construction. So in such cases, there are two hooks. So 180, so L plus 9D for one side and 9D for another side. So L plus 18D. This is for 180 degree bend. Now moving forward, what if there is an overlapping of the bar? So whenever your bars are in overlapping and if the bars are in tension, the extra length is generally taken as 40D plus 9D plus 9D. That becomes 58D, and that is for mild steel bars. If the bars are HYSD bar, we need to add approximately 19% or 18% or 18.5% as elongation. So it will be nearly approximately equals to 68.5D. I hope we are clear about it. And if the bars are in compression, the length will become 45D for mild steels and 68.5 for HYSD steel. So that is for the overlapping of the bars. Now moving forward, the next is bent up bars. Students, generally in slab or in beam reinforcement, this kind of bent up is shown in the drawing or in the practical. If you have bent on the side and if you have seen the steel work, this kind of bent ups are provided. Bent up is generally the same reinforcement bar is at the bottom level, then it is bented up and then it goes at the upper level of the slab or the beam. So that is something known as bent up. The length of the bent up bar is directly considered as 0.45x extra. So L plus 0.45x. Now you might be thinking that what is that x? So that x is, as represented in the figure, that is center to center distance between reinforcement bar. So x is our center to center distance between top level of the reinforcement and the bottom level of the reinforcement bar. The overall the total length will be L plus 0.45x for single bent up. So if there is a 2 times bent up in a single bar, you will taken as 2 into 0.45, so 0.9x. Now how we have derived this 0.45, let us see. So as you can see in the figure, if I formulate the CD, if I want to find out the CD, that will be x upon sine theta minus x upon tan theta. Now the numerator will be common out. So x into 1 divided by sine theta minus 1 divided by tan theta. Here the bent up is generally considered at the angle of 45 degree. That is the ideal condition. In ideal condition, the bent up is provided at the 45 degrees. So theta will be 45. So in the value of the theta will replace 45. So that is how we'll get 0.45x. I hope we are clear about it. This derivation is not your point of concentration. You have to only remember that if there is a bent up in bar, L plus 0.45x is your total length for single bent up. If there are multiple bent ups, you have to add another 0.45 respectively. So I hope you have understood it very well and clear about it. Now moving forward, the next is lateral ties or stirrups. Lateral ties is generally words being used for column. If you have seen a column, in the column work, generally rings are provided. So if those rings binding the vertical reinforcement around the vertical reinforcement, there is a ring of rectangular or whatever shape of the column is, so that is known as lateral ties. And if the same rings are provided in the beam, that is the terminology for that is stirrups. So we need to calculate the length. See, if there is a rectangular column, the ring shape will be also the rectangular, but that rod, that steel reinforcement bar will be the straight. We have to create that rectangular shape by molding the reinforcement bar. So we need to find out the cutting length of that ring. So let us start and understand this figure. So as you can see in the figure, I have provided a beam or the column, whatever you can say, of having total dimension of x cross y. Now, I hope that is the common sense that reinforcement is provided after lefting out the cover distance. So as you can see, this is the stirrup or the lateral tie or the ring. In the site language, it is known as ring. So that is I have shown after the lefting out the cover distance. Now we need to find out the length of this ring. So ultimately that will be 2a plus 2b. A and b are the in dimension of this ring, and if I need to find out the total length of the ring, that is the periphery. So 2a plus 2b, plus there is an hook in this ring, so that is 12d. Okay. Now this length 2a plus 2b or plus 12d or 0.15 meter, whichever is greater, that is the formula. Length of the stirrup bar, the formula is 2a plus 2b plus 12d or 0.15, whichever is greater. So now we need to find out what is a and what is b. So let us understand. Now if I want to find out a equals to, now a is the internal dimension of the ring. In that direction, the total dimension is x. So x minus 2 times the cover. If I deduct the 2 times the cover, I will get at the external surface of the ring. I will be on the external edge of this ring, minus 2 times of that stirrup diameter or that lateral tie diameter. So if I deduct 2 times the diameter of this lateral tie, I will be at the internal point of the ring or the stirrup. So that is the formula for A. X minus 2 times the cover minus 2 times the diameter of bar of the stirrup. And similarly, in the horizontal direction, that is for B. So B equals to Y minus 2 times the diameter of 2 times the cover minus 2 times the diameter of the bar of ring stirrups. Now, once you find out A and B, you have to just put the value in the formula that L equals to 2A plus 2B plus 12D or 0.15. Now here 12D when there is a single side hook. If there is in both the side hook, 2 times 12D, so that will be 24D. So I hope we are clear about the lateral tie. You will find the length. After finding out this length, you need to tell the steel mason or the steel laborer that he needs to prepare a ring of this much dimension in L or B or in the rectangular shape. But first he need to cut the reinforcement bar of this much L length. Moving forward, what if there is a bent up and hook combinedly in the stirrup bar? This is the figure of what I have just told you, that bent up and hook is both are combined in the bar. So you know that for hook we add up 90 degree and for bent up we add up 0.45x. So total length will become L plus 90 plus 0.45. Again, if there is in both the side hook, you have to do 2 times 90. So 18D will be there. Very easy. So I'm moving forward quickly. The next And our last fundamental, which is very important, student, this you need to understand it very well, that is number of bars. Students, generally if you are referring a AutoCAD drawing or if you are referring a manual printed drawing, it is not up to the scale. So you cannot count number of bars from the drawing itself. In column or beam, there are number of reinforcements are provided. But in the slab, if the slab is of 5 meter, then the structural designer or the draftsman is not going to provide you each single reinforcement. So you need to calculate the number of bars. How to calculate? Let us see. First, if the total span where the reinforcement bars are laid out, that is L, so we need to find out the space out of that L. How? That formula is space equals to distance within which the bars are laid. So that is, if the total length of that area is L, so we have to do minus 2 times cover. So L minus 2 times the cover will be the space. Now the formula for the number of bars will be space upon center to center spacing of the bars. Yes, center to center spacing. The center to center spacing, that means if this is 1 bar and this is 2 bar, so center to center distance between these 2 bars. So space upon center to center distance between 2 bars plus 1. Why plus 1? Because it is the simple logic. As you have to prepare 10 columns, you need to prepare number of lines as 11. So there will be 10 columns in your page. So the formula will be L minus 2 times the cover divided by center to center spacing of the bars between 2 bars plus 1. Now, same as the beams are generally 7 meter long, 5 meter long, 10 meter long. So number of stirrups you have to calculate. See, main reinforcement they will give, but number of stirrups, if the distance between stirrup is 10 centimeter or 20 centimeter, in the drawing you are not going to find that this is this is one stirrup, then after 20 centimeter this is another stirrup. You are not going to find like this. So you need to find out number of stirrups as well by having the formula as length of beam minus 2 times of cover divided by center to center spacing between 2 stirrups plus 1. So I hope we are clear about all the fundamentals of reinforcement calculation. Now let us see a numerical based on calculation of RCC beam. Let us see the question first. Determine the quantity of steel, formwork and concrete for a RCC beam shown in figure. Note, take cover size equals to 50 mm all around. Take sizes of stirrups equals to 8 mm diameter at 20 cm spacing and 30 cm spacing at center to center. Clear span of the beam is 7 meter. So here in this numerical we need to find out 3 quantities: formwork, steelwork and concrete work. Let us see the figure first. So as you can see in the figure, a beam is shown that clear span is 7 meter. Now if you can see, there are 2 junctions. These 2 are the column junctions having 30 centimeter in the width, that is 30 centimeter. So between those 2 columns, the clear span of the beam is 7 meter. Now if you can see the section just at the corner of the drawing, the section is of 30 by 60 centimeter or 300 by 600 mm of beam. Now look at closely at the beam. At the top level of the beam, there is a 12 mm reinforcement bar which is known as anchor bars, and the number is written as 2 numbers. So it is written as 2 numbers of 12 mm anchor bars. At the bottom level, there are 5 numbers of 25 mm diameter bars, out of which 2 bars are bent up bar. You can see in the figure there is a bent up at both the ends is provided. So there are 5 numbers of 25 mm bars, and out of 2 are bent up. So remaining 3 are the straight bars. And the stirrup is also shown of 8 mm diameter in the figure, which we have already read in question. So I hope we are clear about the figure. So starting with our first quantity. So the first quantity is concreting or the concrete work in the beam. Now to find out the concrete, all we need to do is we need to multiply numbers L, B and H. Here the beam is one beam, so numbers will be 1. Now B and H, we also know that B and H are the section 30 by 60, so 0.3 cross 0.6. Now we are talking about the length. So as highlighted in the drawing below, the length will be clear span plus both the column junction. Students, this is one of the important aspect of the concept, that these two column junction, this is the beam and these two are the column junctions. So these column junctions will be concreted at the time of the beam slab concreting. So 30 centimeter this and 30 centimeter this. So now the concreting span, beam span is 7, but I am talking about the concreting length, that will be 7.6. So we'll get the quantity as 1.37 cubic meter. So that was for concrete. Now let us look at for the formwork. So talking about the formwork, I have divided the formwork quantity into 3 parts: the beam bottom, beam sides and the beam corners. So there will be the formwork will be placed at 3 different points. First we are talking about the bottom of the formwork. Now formwork is a 2-dimensional quantity. Students, formwork is always measured in the meter square or square feet. So formwork for beam bottom. Now if you are talking about the bottom, in the bottom aspect you will see the width and the length. So length of that bottom will be equal to the clear span of the beam, because here there are 2 column junctions. So beam bottom will be between those 2 junctions, that is 7 meter, and this width, that width is equals to the beam width, that is 0.3. Now sides of the beam. Now if you are talking about the sides of the beam, that will be also in the length nearly equal to the beam length. But here, if these 2 are the column junctions, this will cover, the length will cover this. That means while calculating the beam sides, we need to cover that column junction portion. So length will be 7.6. Now beams, if we are talking about the beam side, that is the height. So height is beam depth 0.6. Now ends are the 2 rectangles. So that is 0.3 cross 0.6. So that is how we'll get the formwork quantity as 11.58 meter square. So I hope we are clear about it. Now the third and the most important quantity, that is reinforcement work. Let us see. First we'll calculate for 12 mm horizontal bars which are at the top level of the beam. Now we know the formula, that length of the 12 mm bar. How we'll find it? As we know the total span of the beam is 7.6. Is if you go back to the slide and see the drawing. So as you can see, the total span of the reinforcement is including the column junctions. That is total span 7.6 plus 2 times hook. There are 2 times hook. There is a 180-degree hook both the end of the bar. So plus 18D. Now this reinforcement is placed just inside of the beam. So that will be cover So minus 2 times of cover. So the length of the bar will be 7.6 minus 2 times of cover. Cover was 50 mm all around. That means total cover is 50. So both the ends 25 mm plus 2 times the 9D. Here the D is diameter, that is 12 mm. So we'll get the length as 7.77 meter. Now in the column of numbers I have written 2 because in the drawing we were given that there are two 12 mm bars. Now the length we have found out 7.77. But in the column of B and H, we don't have to write width and height because for the reinforcement, there is no width and height. So in the column of B, I have written @ and in the column of H, I have written the formula of D square by 162. Here the D is 12 mm. So 12 square by 162, that is 0.89 kg per meter. Now I have the weight of 12 mm bar per meter, 0.89. I have the length and the numbers. So I multiply all these things and get the weight of the horizontal 12 mm bar as 13.83 kg. I hope we are clear about this. Now doing the same calculation for the bottom level 25 mm bar in which 2 were bent up. That means 3 were straight. So applying the same logic that total length is 7.6 minus 2 times the cover plus 2 times the 9D. But here the D is 25 mm. So we'll get the length as 8 meter. So now numbers is 3, length is 8 meter, and for 25 mm, 25 square by 162 will be 3.86 kg per meter. So we'll get the weight for 25 mm straight bars as 92.64 kg. Moving forward, now we need to calculate for the 25 mm bent up bars. We have already learned the fundamental that bent up bars length of the bent up bars are L plus 0.45x. Here there are two bent up bars, so we'll have to take L plus 0.90x. Students, now understand this figure. So as you can see here, we need to find out x. To find out the x, that the bent up bar is in the beam. So the total depth of the beam minus 2 times the cover minus half diameter from the top side and half diameter from the bottom side, as I have highlighted in the figure. That is how we can get that center to center distance of x. I hope we are clear about it. Let us see in the calculation. The length of the bar will be 8 meter. Why? Because we are finding it for 25 mm. So in case of 25 mm bar, the straight length was 8. Now if that 8 meter length bar is bented up, so it will be 8 plus something, 8 plus 0.90x. So L will be 8 plus 0.90x. Now to find out x, we have just learned that x will be 0.6 minus 2 times the cover and minus 2 times the half diameter of that bent up bar length. So we'll get the x as 0.51 meter. Now replacing with that value in the formula L plus 0.90x, we'll get the new length as 8.46. So there were two bent up bars and that is 8.46. So we'll get the weight of the bar as 65.30 kg. I hope we are clear up to this point. Now only stirrups are left. Let us see. So we know the formula of the number of stirrups, that span of stirrups divided by spacing of stirrups plus 1. But here, coming back to the drawing, as you can see, here the spacing are 3 different spacing. Initial 20 centimeters center to center, at center portion 30 centimeter center to center, and at last portion again 20 centimeter center to center. So we need to find out first for that both the ends 20 centimeter and that center 30 centimeter. So first, starting with the 20 centimeter at the one end, here the length or the span of spacing is 0.3, that column junction, plus 1.5, the 20 centimeter span is given, minus 0.1, because at that end the 10 centimeter gap is left out. So 0.3 plus 1.5 minus 0.1. So we'll get the span as 1.7 meter and the spacing is 20 centimeter. So writing out the formula, we'll get the numbers as 10. This is for the one side. At the other end, that is again 20 centimeter. So we can double it. So at the the total stirrups will be 20 numbers. Now let us see for the 30 centimeter spacing. For 30 centimeter spacing, as you can see, the span will be 4 meter. The clear span is 7 minus 1.5, 1.5 both the end. So 4 meter will be the span, 30 centimeter with the spacing. So we'll get the numbers as 14. Here I have not considered plus 1 because in the one beam you can only do plus 1 for one time only. So we have already done in the 20 centimeter. So at the center portion we don't need to have that plus 1. So we'll get the number of stirrups for 30 centimeter spacing as 14 and at the ends that is 20. So total number of stirrups are 34. Now we need to find out the length of the stirrup bars. Let us see. We know the formula for the length, that 2a plus 2b plus 12d or 24d, if there is a two side of or 12d or 0.15d or 0.15 meter, whichever is greater. Now we need to find out the A. A is x which is vertical total depth of the beam minus 2 times cover minus 2 times the diameter of stirrups. B is the horizontal dimension of the beam minus 2 times cover 2 times diameter of the reinforcement stirrup bar. So that is how we'll get A and B as 0.234 and 0.534. Now putting that in the formula of the length, we'll get the total length of the stirrup bar as 1.69 meter. Numbers were 34. This is 1.69. Now d square by 162. 8 square by 162. That is 0.39 kg per meter cube. So we'll get the kg per meter. So we'll get the weight as 22.41 kg. Here you don't have to add up the steel. You don't have to write the total quantity. You have to write out the quantity as individual diameter for 25, for 12 and for 8 as I have represented here. So I hope we are clear in the RCC beam calculation. So this is it. That was all about in today's session. In case of any query or doubt, you can always contact me on my mail or my number. Thank you.